This
Today's session,
conference will now be
we
recorded.
have started discussing things with respect to the UART protocol in the previous class. So we looked into the introduction of the UART protocol. So we so far have learned UART communication protocol. We saw its features of the UART communication protocol and how is the data transmission and reception happening between the two devices. We saw with the practical program as well. Then after that, we started with SPI communication protocol. We saw the features of the SPI protocol, the lines which are available in this protocol, the hardware configuration, and we started with the data transmission. We saw how data gets transmitted in the SPI communication protocol and data validity. Also, when to choose a normal configuration, when to choose daisy chain configuration, and how to write a particular slave with the specific data in the daisy chain configuration. So that much we discussed in SPI. Because there was no chip which supported SPI communication protocol on our board, we didn't have any practical example to be learning it. So we then move to the I2C communication protocol. It is nothing but inter-integrated circuit. This is a communication protocol which was introduced by the Philips company, which is now called as NXP. We started with the features of the communication protocol. It's a synchronous half duplex protocol. And the special feature of I2C is multi-master, multi-slave, which is why we make use of I2C more than SPI. Even though SPI is 20 times better or faster than SPI, people still prefer I2C itself because of the feature of multi-master, multi-slave. Then we started learning things with respect to the bus features in the I2C protocol. We will have two buses. One is with respect to the data transmission, the other one for the clock. Then all the devices in the network are software addressable. So this communication protocol supports multi-master with collision detection. The buses are serial buses. It's 8-bit oriented. Generally, all the masters and the slaves will be 8-bit oriented, but there are some of the slaves which might work on 16-bit orientation also. So we have bidirectional bus with 4 different modes. And because of the extensive usage of I2C communication protocol, we have on-chip filtering on the data lines these days. Then we started with the examples, then the signal and the complete data transfer. So now to start with, we have two lines. One is the data line, the other one is the clock line. So whatever is transmitted on the data line will initially be visible for all the devices in the network. So to make sure the communication is happening between a master and a slave, master is going to transmit the unique address of the slave, which will be obtained on the data sheet of the slave, and that will be given by the manufacturer. So whichever slave gets matched with the unique address, so that slave responds back and the communication between the master and the slave is going to happen. So this network may have multiple masters, and the masters are master capable as well as slave capable, and all other devices are just the slaves. You consider a device as a master or a slave depending on the clock pulses generations capability. Now if a device has the capability to generate the clock pulse, then you call it as a master. If the device doesn't have the capability to generate the clock pulse, you call it as a slave. Then we saw two wire interfacing SD and SCL line. We saw the wired and concept. So in case of wired and concept, if the wire or if the cable, if the line is not being used, every device in the network is going to read a 1. And if there is any data transmission happening, or if the line is being used, all the devices in the network ends up reading a 0. Half of the concept we achieve with the help of wiring, the other half we are going to achieve with the help of AND. So we saw the same happening on both SCL and SDA line. Then we saw the conditions and data validity. So what triggering is I2C communication protocol? It's a synchronous communication protocol, but what triggering is used on the clock pulse? Yes, it's the level triggered communication protocol. So either the transmission or the reception happens at the levels of the clock pulse. Now at the low level, all the devices are going to transmit the data. Whoever has to transmit will transmit the data at the low level of the clock pulse. And that is why you see the change of data in the data line. It can either be a 0 or a 1. And if the clock pulse is high, all the devices in the network are going to read the data. That is why you don't see a change of the data line. So 0 is maintained as 0, is 1 is maintained as 1. But at the high level of the clock pulse, if there is any change of data line seen, then it represents a special condition. So if the clock line is high and data line is falling from high level to low level, you call it as the start condition. And if the clock line is high and data line is going from low level to high level, we call it as stop condition. So we may require start and stop condition here because to seek the attention of the receiver. Even though it's a synchronous communication protocol, there are chances when the slaves must have been sleeping to save some power, or they must have been busy doing some other task. So it is important to monitor to seek the attention before the data transmission happens. So we will have a start or a stop bit transmitted. Okay, if D1 out is equal to 1, then remaining are going to get 0. Means communication only with that slave and remaining slave off in the wired AND. So if, okay, Syed, if D1 out is going to receive a 1, okay, so that represents the data line. So D1 out, you are not getting 1, you are writing a 1, okay. Then remaining gets, yes, all other devices in the network are going to get a 0 from the data line. That is representing the line is being busy and somebody is using that data line. So whichever has got the communication established will continue to communicate. All other devices in the network will not start or initiate the communication until they read a 1 from the data line. So they will not be off. All other slaves in the network will actually be busy with their own task, or maybe they might go to the sleep mode to save some power. Now again and again you have to come if there is a communication to happen. Again and again the masters, it is always the masters who initiate the communication. So masters should come and check whether the data line is giving a 1 or a 0. Depending on that, it has to decide to take the action. Okay. All right. Now let us proceed with the next topic. So how data gets transmitted on the SDA line, how clocking on the SCL line happens, what is clock synchronization, and what is data arbitration. Now to make you understand the data on the SDA line, let me take an example. So what type of communication protocol is I2C? To which category the I2C belongs? Yes, it's an intra-board protocol. Now, what do you mean by intra-board protocol? What do you mean by intra-board protocol? Yes, so communication should happen between the two chips of the same board. Okay, so communication should happen between the two chips of the same board. Now, we have a chip on our board which supports I2C communication protocol, and that is nothing but the RTC. So RTC here is a peripheral, it's a chip. Okay, RTC here is a chip which supports I2C communication protocol, and obviously our microcontroller also supports I2C communication protocol. Now you want to establish the communication between the microcontroller and the RTC. So that is what I have to establish. I have to communicate between the PIC16F877A microcontroller and the RTC, which are available on our board. Okay. So what we have to do is, first and the foremost thing, we are going to start with the requirement. So I have to establish the communication between the PIC microcontroller and the RTC. Now to establish the communication, let me represent it on my page right now. So I have a microcontroller. So this one is the PIC16F877A microcontroller, and this one is the RTC. Okay. So how many lines are available between the two devices in I2C communication protocol? Yes, two lines. One with respect to the clock line, the other one is the data line. Now, what is the direction of clock line? What is the direction of the clock line? Is it a bidirectional line? So yes, the direction should always be from the master to the slave. So master is always the microcontroller. So assume this is the master. So it is the PIC16F877A microcontroller. Let me highlight it here. It is PIC16F877A microcontroller, who is right now acting as a master. So this one is a master now. Okay. So this is your RTC, and RTC is not capable of generating the clock pulse. So this is acting as a slave right now. So this one is a slave right now. So this is master and this one is the slave. Now coming to the direction. Okay, I'll tell what RTC does. So as of now, I'll briefly give an introduction. So this is the clock line. So clock line always goes from the master to the slave. So let me write the clock line's name as SCL. So SCL from master goes to the slave. So slave also you can take SCL itself, and the name can vary from one manufacturer to another. So data line, I take it as SDA, and it's actually, what is the direction? So this is SDA, and the SDA lines are bidirectional lines. So you have to achieve half duplexity, where communication happens between the two chips, and only one can communicate at the time. Okay, so both can communicate. There is a two-way communication, but only one can communicate at a time. Now, what do I need to provide to the SDA line? So what do I need to provide to the SDA line? We saw it in the previous class. No. So first of all, to make sure SDA line is a 1 or a 0, if the connection is not established, what should I do? I have to add a pull-up circuit. Okay, and that is required for the SCL line also. So I'm adding two pull-up circuits for the SDA and the SCL line. Okay, so this is VDD. Okay, I'm going to add resistors. Okay, so like this, I'm going to add the resistors. Okay, So I have got the resistors added. Now, let me give you a small requirement. So RTC stands for real time clock, and the task of the RTC always is to calculate the running time. Okay, so RTC is nothing but real time clock, and the task of the RTC is always to calculate the running time. Okay, I have a master, the PIC16F877A microcontroller, who is capable of generating the clock pulse. So when it comes to the RTC, it is a chip which is capable of generating the, it is capable of actually counting the time. So you need not use the timers. You can use RTC to calculate the time, and this RTC will have the data regarding time. So RTC will have registers which is storing the number of seconds. RTC will have registers which is storing the number of minutes. RTC will have registers which is storing number of hours. Also, it stores the week of the day, it stores the date, it stores the month, it stores the year. So RTC is nothing but real time clock which is storing the time. Okay. Now generally what happens in the RTC is there will be registers to store these value. Now more about RTC we will discuss when we go with the let's say the programming part. So I'm going to say RTC is going to have the registers to have the data stored. Okay. Now, each registers are available in different addresses. Let me give some simple scenario. Address 0x00 will be used to store the number of seconds. Okay. So there might have been a register in the address 0x00 to store the number of seconds. There must have been an address there must have been an address 0x01, okay, which is storing the number of minutes. Okay, so addresses can vary. I'm just giving an example. There must have been a register in the address 0x02 which is storing the number of hours. Okay, so there must have been a register in the address 0x00 storing number of seconds. So register 0x01 storing number of minutes. Register 0x02 storing number of hours. Okay, so now what happens is the task given to you is you are supposed to read this time from the RTC and you have to get it displayed on the CLCD. Okay, you have to read this time from the RTC and get it displayed on the CLCD. You being the microcontroller should read the number of seconds in the RTC and get it displayed on the CLCD. So that is your task. Okay, now I will not read everything. Assume I want to read just the number of seconds from the RTC and get it displayed on the CLCD. Okay, I just want to read the number of seconds from the RTC and get it displayed on the CLCD. Are you able to understand the requirement? So your microcontroller should go to the RTC, read the number of seconds and come back, display it on the CLCD. Now the communication is happening between two chips of the same board, and I am going to make use of I2C communication protocol. What will be the very first step in the communication protocol? What will be the very step in the I2C communication protocol? So assume clock pulse is generated. What should be the very first step? Come on, in the communication protocol, do I directly start transmitting the data? No, right? Yes, SDA is equal to 1. That means I have to check if the bus is idle or not, correct? Check if bus is idle or not. So you have to check whether the bus is idle or not, whether I'm able to use the bus for the communication of the data. I have to check. That is my first step. I have to check if the bus is idle or not. Now, how will I check if the bus is idle or not? How will I check if the bus is idle or not? Come on. Yes. So if SDA line is giving me the value 1, it represents the bus has been idle. Now assume you identified that the bus is idle. Okay. You identified that the bus is idle. What will be the second step? After you identify whether the bus is idle, what will be the second step? Do I transmit the address directly? What should be the second step? Okay, before transmitting the address, what should I make sure? I have to seek the attention of the receiver, isn't it? I have to transmit a start bit in order to seek the attention of the receiver. Maybe RTC is sleeping or RTC is busy doing some other task. I have to seek the attention of the RTC. So I'm going to transmit a start bit. Okay. Now, you have seeken the attention of the receiver. So our receiver, that is RTC, is paying attention to you. What is the next step now? What is the next step? Come on. What will be the next step now? You have taken the attention of the receiver. Yes. So this time you have to transmit the unique address of the RTC. Okay. You have to transmit the unique address of the RTC. Now, when I'm transmitting the unique address of the RTC, who and all in the network will be able to receive it? After I transmit the unique address of the RTC? Yes. So, everybody in the network is going to receive it. But who is going to respond back? Who is going to respond back? It's the RTC who is responding back. So, generally, once you're done transmitting the unique address, you can expect an acknowledgement from the RTC. Correct? You can expect an acknowledgement from the RTC. Now, only after you receive the acknowledgement from the RTC, so what master does is, master starts transmitting the data. I mean, master starts communicating. Master starts communicating with RTC. And once the communication is done, what is the master going to do? Once the communication is done, yes, master is also going to transmit a stop bit. Okay, so these are the procedures you are going to follow. Stop bit. So first you have to check if the bus is idle or not. You're going to transmit a start bit. Then you transmit the unique address of the RTC. Then after the unique address is transmitted, you're going to receive the acknowledgement from the RTC. Master starts communicating with the RTC. Then you are going to transmit a stop bit. That is, the master transmits the stop bit once the communication is completed. Are you able to follow this? Okay. But there is a small problem here in the step. Okay, the steps we are following, we have a small problem. Now, what is the problem is, when the master is going to the slave, it can either be for the purpose of reading or it can be for the purpose of writing, right? So master can go to the RTC to write some data into its registers. Master can go to the RTC and request for some data from its registers, correct? So master can go to the RTC either for the purpose of writing or for the purpose of reading. Are you able to follow this? So master is not only transmitting. So master can also read the data from the slave. Master may go to the RTC either for the purpose of reading or for the purpose of writing. Now, did I ever say the RTC what was my purpose? Did I ever say the RTC? No. And that is always a critical step to say whether you came to the RTC for the purpose of reading or for the purpose of writing. Now that is done something like this. First you are going to check if the bus is idle or not. Then transmit the start bit. Now who is transmitting the start bit? Who is transmitting the start bit here? It's the master who is transmitting the start bit. Okay. So it's the master who is going to transmit the start bit. Let me rephrase the steps again. So the very first step is master is going to check if the bus is idle or not. Check if bus is free. Okay. So that is the first step. Master is going to check if the bus is been free. Now after it identifies the bus is free, it is going to transmit a start bit. So master is the transmitter and your RTC is the receiver. Okay. Now initially master is the transmitter and RTC is the receiver. Okay. So direction is from the master to the slave right now. After the start bit, your master is going to transmit the unique address of the RTC. Okay. So I'm going to transmit the unique address of the RTC, which will be available on the data sheet of the RTC. I'm going to transmit the unique address of the RTC. And generally, unique address of the RTC will most probably of 8 bits. Okay. So generally, it will be of 7 bits. The unique address of the RTC will be generally of 7 bits. So I'm not going to just transmit the address of the RTC. Along with the address of the RTC, I also transmit the intention of me going to the RTC. So I'm going to say my intention, whether I'm coming to the RTC for the purpose of reading or for the purpose of writing. Okay, so I'm going to inform the RTC with an intention. Along with the 7 bits, I'm going to specify the intention. Now, when RTC receives that unique address, also the intention, first it identifies that the unique address it has received is its own, and after that, looking at the LSB bit, it will analyze whether the master is coming for the purpose of reading or for the purpose of writing. Okay, one bit is dedicated for the intention when you are transmitting the unique address to specify whether you are going to the RTC for the purpose of reading or for the purpose of writing. Okay, so now it is still the master being the transmitter. Now, what is actually my intention of going to the RTC? What is my intention of going to the RTC? Whether I'm going for the purpose of reading or for the purpose of writing. I have to read the number of seconds. Okay, so I have to read the number of seconds. Okay. Now, after receiving the intention and the unique address, the next step is the acknowledgement will be given from the RTC. Okay, acknowledgement will be given from the RTC. Now, who is the transmitter? Acknowledgement is given from the RTC. So, your RTC is the transmitter when acknowledgement is being given, and that acknowledgement is being received by the receiver, that is your master. So master is the receiver right now. Okay, acknowledgement is given by the master, sorry, it is given by the RTC. So now RTC is the transmitter and master is the receiver. Now once the acknowledgement is received, what will be the next step? What will be the next step? How many registers RTC is going to have? Communication should establish, correct? So communication means master should go to the RTC and read the number of seconds. Now how many registers are available in the RTC? Do I have only seconds stored in the RTC or multiple registers are there? Do I have a single register storing only the number of seconds? As of now, I have listed 3, but there are multiple registers in the RTC. You said you are going to the RTC to read, but did you tell from which register are you going to read? You told the RTC you're going to read. Did you tell from which register you're going to read? No, you haven't said it again. So, you have to now first say from which register you are going to read the data. So, the master transmits the register of master transmits the address of second register. Correct? Master is going to transmit the address of the second register. So in this case, master is the transmitter and slave is the receiver. So master is transmitting the address of the second register. So master is the transmitter and slave is the receiver. Now after you are done transmitting the second register, it is expected that you may get an acknowledgement from the slave. Okay, it is possible that acknowledgement is received from the slave. Acknowledgement, I would say, possible, not exactly. So you may expect the acknowledgement from the slave. Okay, so acknowledgement from the slave is possible. Whatever previous acknowledgement you saw from the RTC, it's a must. So this acknowledgement is a must. But the acknowledgement what you receive later when master is transmitting the address of the second register, acknowledgement is possible. Now if RTC receives the second register's address, it understands that the master is coming to the RTC to read the number of seconds. What should be the next step? After slave understands master has come to me to read the number of seconds, what will your slave do? What will your slave do? It is going to send the number of seconds in the register. Okay. So RTC gives number of seconds in the register. Now who is the transmitter? Who is the transmitter this time? Yes, it's RTC being the transmitter and master being the slave. So RTC transmits the number of seconds and slave is going, sorry, your master is going to receive the number of seconds. Now after reading the number of seconds, again it is possible that your master is giving an acknowledgement. Okay, so your master is giving an acknowledgement, but that is not compulsory. It is possible because you may think I am the master, why should I give the acknowledgement? Once I'm done reading, I'm done. Why should I say that I'm done reading? So you may think like that. So masters are that way. Master may give an acknowledgement. If the master is polite enough, master may give the acknowledgement saying, I'm done reading the number of seconds or I have received the number of seconds. Now that I have received the number of seconds, I will display it on the CLCD and I'm going to transmit a stop bit. So first, master is going to check if the bus is free. Second, start bit gets transmitted. Third, unique address of the RTC along with the intention will be transmitted. So master is the transmitter and the RTC is the receiver. Then acknowledgement from the RTC will be given. So RTC will be the transmitter and master will be the receiver. And acknowledgement this time from the RTC is a must. Now master transmits the address of the second register because master wants to read the data from the second register. So master is the transmitter and RTC is the receiver right now. Now, once master transmits the second register's address, it is possible that the master may receive the acknowledgement from the slave saying that I got to know that you are coming to me to read the second register. Now, after that, RTC starts transmitting the number of seconds from the second register, and that will be received by the master. And it is possible that master gives an acknowledgement saying that I got the number of seconds from you. Then the communication is done, and the stop bits will be transmitted by the master. Acknowledgement or stop bit with the master will be sent. It depends on the master. So acknowledge, yeah. So here this acknowledgement will be given by the master, and stop bit is also given by the master. So this is how communication happens between two chips of the same board. These are the steps it is going to follow while the communication is established. Any doubts in this? Okay, make a note of this. We will proceed. Okay. Hmm. So whenever the address from the master is sent, acknowledgement from the slave is a must. Yes. So at the very first stage, when the master is giving the address of a particular slave, so it is very necessary that the acknowledgement is received. Only when the acknowledgement is received, you can establish the communication. If the acknowledgement is not received, there is no confirmation that the slave has received the address, and there is no confirmation that the slave has still been active in the network. So we have to make sure the acknowledgement is received when the unique address is given to the unique address of the slave is being transmitted. Okay. I2C is multi-slave means, now in this example, another microcontroller as master can access the RTC right as per the I2C's definition. No. So what I2C, like obviously multiple masters will be there who can communicate with multiple other slaves. So RTC can be accessed, can be communicated by another master also in the network, but not at the same time. So I can have multiple masters in my network. There can be some other microcontroller. Assume there is an ARM microcontroller who wants to communicate with the RTC. It is possible. But the communication happens only when RTC is available to that microcontroller. Clear? But when another microcontroller accessing RTC, our pig becomes silent, right? Also becomes slave as only one data line you are saying. Okay. See, if the communication is already happening, then another microcontroller cannot come and access the RTC. If the PIC is already communicating with the RTC, at the same time another device cannot access the RTC. Okay. So it is a single data line. Only two can communicate at the same time. One master and one slave can communicate at the same time. So if a master and a slave is already communicating, is already using that data line, obviously all other devices in the network should be silent. They cannot uh, communicate as the data line is already being occupied. Okay. All right. Let us proceed. So the same we are going to observe here. Okay, with the let's say 1 second. I'm going to manage it like this. Okay. So I hope you can observe. So I'm representing it like this. One second. I'm just trying to represent both the things together. Okay. So I'm just trying to set this up. And this one. Okay. Now I'm just showing the pictorial representation of this communication happening. And every communication in case of I2C protocol happens with respect to the clock pulse. And it's a level triggered communication protocol. So always you're going to either transmit the data or receive the data at the levels of the clock pulse, either the low level or the high level. Now, first and the foremost thing, when the communication has to be established, the microcontroller first generates a clock pulse. Now, assume the clock pulse being generated by the microcontroller is a high signal. So, it's a high level. Now, at the high level of the clock pulse, so my master, being the transmitter, is going to first transmit a start bit. So you can observe that there is a start bit being transmitted at the high level of the clock pulse by the transmitter. The first data line what you are seeing is the transmitter. Okay. So it is the master's data line. The first SDA you are seeing is the master's data line. So first, when the clock pulse is high, master is going to transmit the start pulse. Now, master is going to generate 8 clock pulses, one after the other obviously. It generates 8 clock pulses. Now assume the master is done giving the unique address of the RTC, and also assume slave is done giving the acknowledgement back. Okay, so that's an assumption you have to make. So assume master is done giving the unique address and the intention. So step number 3 is done, and step number 4 should be the acknowledgement being given by the RTC. So assume that is also done. Okay, next step number 5 is master should transmit the address of the second register. Okay, master is going to transmit the address of the second register. So second register's address, assume it is of 8 bits. So master is going to transmit the second register's address. Okay, and that is always at the low level of the clock pulse. So for every low level of the clock pulse, master transmits the second register's address. Now similarly at the same time, receiver is going to receive the second register's address. Okay, so receiver here, the second SDA line what you see is with respect to the receiver, that is the slave. So receiver is going to receive the second register's address. So let me note it down. So first SDA line is with respect to the master, second SDA line is with respect to the slave. Okay, so first SDA line is with respect to the master and second SDA line is with respect to the slave.
We'll check pricing.
Okay. Now, master transmitted the second register's address in the first 8 clock pulse. Slave read that second register's address in the same first 8 clock pulse. So there is no change of data. Whatever is transmitted is received by the slave. Now, what should the slave do is, possibly it has to give an acknowledgement. Okay, slave has to give an acknowledgement. Now, how the acknowledgement is given is, at the high level of the clock pulse, whoever should be giving the acknowledgement is going to transmit a 0. Okay, so at the high level of the clock pulse, whoever wants to give an acknowledgement is going to transmit a 0. So receiver is going to pull the data line low by representing that I have received the data whatever the transmitter is transmitting. So acknowledgement is being given. Next, so after the acknowledgement is given, what is the next step? RTC should give the number of seconds to the master. Now RTC changes to be the transmitter and master changes to be the receiver. Okay, so you can see RTC is the transmitter now and master is the receiver now. Now master generates the next 8 clock pulse. RTC transmits the value from the second register. So whatever RTC is there, so it is going to transmit the second register's address. Sorry, second register's value. Now once it is done transmitting the second register's value, master should give the acknowledgement. So master is giving the acknowledgement by pulling the line low at the 9th clock pulse. Okay. So actually acknowledgement will not be given just by the receiver. The transmitter also gives an acknowledgement saying I'm done transmitting the data. So if you observe here in the very first line, so let me repeat this. So first start bit gets transmitted by the master, then master generates 8 clock pulse. So then master transmits the second register's address and it pulls the line up representing I'm done transmitting the data. Now the slave, being the receiver, reads the second register's address and pulls the line low representing it has received the second register's address. Now the transmitter and receiver are going to get interchanged because RTC should now give the value from the second register. Now RTC turns out to be the transmitter and master is going to be the receiver. Now master generates 8 more clock pulses. RTC transmits the second register's value and pulls the line up at the 9th clock pulse representing it is done giving the data. After that, the master being the receiver receives the second register's value and pulls the line low at the 9th clock pulse representing it has received the data. Then at the high clock pulse, once the communication is done, it is in fact the master who transmits the stop bit. Understood this signal flow? Acknowledgement making 9th clock pulse high. Not the clock pulse, it is the data line. So at the high level of the 9th clock pulse, the line will be pulled up by the transmitter and line will be pulled low by the receiver. So that is the acknowledgement. Understood this? Okay. But when you see the communication between the master and the slave, do you see two different data lines to the master to the slave? Do you see two different data lines? Come on, are there two different data lines for the transmitter and the receiver? No, there is only one data line. At the high pulse, data gets transmitted. At the low pulse, data gets received. Okay, sorry, I said it interchangeably. At the low level, data gets transmitted. At the high level, data gets read. So, because I don't have two different data lines, I have a single data line. So this is what you get to see in the actual data line. And this is the AND of the two data lines of the master and the slave. You can see so here whatever you AND with 1 remains the same. Okay. Anything you AND with 0 becomes a 0. Whatever you AND with 1 remains the same. Anything you AND with 0 remains to be 0. And at the last, what you see is a stop pulse, or it can be repeat start also. If you want to continue to communicate, you can go for a repeat start. So this is the signal what you observe at the end of the actual SDA line. Is that clear? Okay. And here in the I2C communication protocol, so we call 0 as the dominating bit because anything AND with 0, it makes the 0 to be represented. We call it as a dominating bit. And whatever I'm representing here right now, we will achieve the same in the programming going ahead. Okay. Whatever I'm showing here right now, we will achieve the same going ahead in the programming part later. Okay, I have a doubt from somebody. Ma'am, please repeat what happens at the low level and high level of the clock and the data line both. Okay. Now I will explain this signal diagram again. Okay. So what happens is, whenever there is a clock pulse generated at the low level of the clock pulse, you know the data validity here. At the low level of the clock pulse, always the data is transmitted, and at the high level of the clock pulse, always the data is read. Okay. At the low level of the clock pulse, data is transmitted. At the high level of the clock pulse, data is read. Now observe what happens in this case. Okay. So first and the foremost thing, clock pulse is always, it will be generated from the master itself. Okay, from master or slave. So whether it is the master or the slave, whoever has to transmit the data will transmit at the high level of the clock pulse, sorry, low level of the clock pulse. Whoever is receiving will receive at the low level of the, oh, I'm very sorry, I'm saying it. So whether it's the master or the slave doesn't matter. So whoever is transmitting will transmit the data always at the low level of the clock pulse, and will read the data always at the high level of the clock pulse. So doesn't matter whether master is transmitting or slave is transmitting, or whether master is receiving or slave is receiving. So whoever is going to transmit will transmit at the low level of the clock pulse. Whoever is receiving will receive at the high level of the clock pulse. Now first clock pulse always gets generated by the master. So clock pulse gets generated. Now assume after the start bit, so clock pulse gets generated by the master. There are 8 clock pulses being generated because I have to transmit 8 bits of data. So 8 clock pulses gets generated like this. Okay. Now first task is for the master to start the communication. Assume the acknowledge master is done giving the unique address of the RTC, and assume slave is done receiving the slave is done giving the acknowledgement to the master. So my next step is, master should transmit the second register's address. Now the first data line what you see is with respect to the master. So master transmits the second register's address at every low level of the clock pulse. One bit will be transmitted. At the same time, slave is going to receive that data at the high level of the clock pulse. So like this. Okay. What happens is, at low level, one bit of the data will be transmitted. At high level, one bit of the data will be read by the receiver. Again, at low level, one bit will be transmitted. At high level, one bit will be read. So like this, 8 bits of data gets transmitted in 8 clock pulse. The same 8 bits of data gets read by the receiver in the same 8 clock pulse. Okay. At the 9th clock pulse, okay, low write, high read, correct. So at the low level data is transmitted, at the high level data is read. Now after transmitting 8 bits of data, at the 9th clock pulse you have to give the acknowledgement. So first transmitter gives the acknowledgement saying that it is done giving the data. Then receiver gives the acknowledgement saying I'm done receiving the data. So acknowledgement is given by the transmitter by pulling the line up. Acknowledgement will be given by the receiver by pulling the line low. Okay. So data line will be pulled up by the transmitter. Data line will be pulled low by the receiver when they have to give the acknowledgement. Now RTC is done receiving the number of seconds. Sorry, RTC is done receiving the address of the second register. Now RTC should give the value in the second register. So now 8 more clock pulses gets generated by the master. Now RTC is the transmitter and master is the receiver. So RTC is transmitting, master is receiving. You can see the change. RTC is transmitting. It's the transmitter here. Okay, you can observe it's the transmitter here. Slave is the receiver here. Now RTC transmits the data from the second register in the first 8 clock pulse. Okay, so at the low level, RTC transmits 1 bit. At the high level, master receives that 1 bit. Again, at the low level, RTC transmits 1 bit. At the high level, master receives 1 more bit. So RTC is the transmitter and your master is the receiver. RTC is transmitting the second register's value, and at the 9th clock pulse, it should give the acknowledgement saying it is done giving the data. So it pulls the line up, and at the same 9th clock pulse, the microcontroller being the receiver pulls the line low, representing it is done receiving the data. So after that, you are going to get a stop bit transmitted. Generally, it's the master who transmits the stop bit, or whoever is the transmitter at the end is going to transmit a stop bit. But we don't have two independent data lines associated to the master and the slave. It's half duplexity, and both master and slave are communicating using the same data line. It's a bidirectional data line. So it is always an AND which happens at the end. What you see at the SDA's actual data line is this. It is the AND operation. So here you can see anything AND with 1 remains the same. Okay, because 0 AND with 1 is a 0, 1 AND with 1 is a 1. So whatever bit you AND with 1 remains the same. Whatever bit you AND with 0 turns out to be a 0. Again, whatever bit you AND with 1, you get to see the same data. Whatever bit you AND with 0, you are going to see a 0. And at the end, what you see is a stop bit if you want to stop the communication, or repeat start if you want to continue the communication. So this is what you see at the end of the data line. You said stop bit is when clock is high and data rise from 0 to 1. But where is it in the diagram? So you can see clock line is high. Okay. So clock line is high. So if it is repeat start, you are going to transmit a start bit. When the clock line is high, you transmit a start bit, that is repeat start. Let me highlight here. So clock line is high, you can see. And to stop the communication, the signal should go from low level to high level. This is stop. If it is repeat start, when the clock line is high, again you see a data transition from high level to low level. So that is repeat start. This. So you can either stop the communication or do the repeat start. Understood this? Okay. So the next we have got is clock pulses generation. You can make a note of this if you require. I'm going to continue in 1 minute. Okay, done. Can we continue? Okay. So the next we have is clocking on the SCL line. Now, whatever we are discussing with respect to clocking is when two masters are trying to communicate at the same time. So, first we are talking about clocking on the SCL line. Okay. Now, assume there are two masters communicating at the same time. So, two masters are communicating at the same time. Okay. Now, when do I say a device as a master? When do I generally say the device is a master? Yes. So, if the device is able to generate the clock pulse, then you call such devices as a master. Okay. Now, I have taken a network where there are two masters and they want to communicate with each other. So, assume there is one microcontroller and another microcontroller. So, I have two microcontrollers trying to communicate with each other. Now, both the microcontrollers cannot behave as a master because there is only one clock line and only one can generate the clock pulse. I don't have two different clock lines. There is only one clock line and only one microcontroller can generate the clock pulse. Now, assume microcontroller 1 is behaving as a master and microcontroller 2 is behaving as a slave. So microcontroller 2 is master capable as well as slave capable. But in a network, there can only be a single master and a single slave. I mean, multiple slaves obviously in the network, but communication happens between a single master and a single slave. So microcontroller 1 is behaving as a master and microcontroller 2, it is master capable, but just for the sake of this communication, it is behaving as a slave. Okay. And the communication between two has got established. Assume the communication has started between the two devices. Communication has started like this between the two devices. Now, microcontroller 1 generates the clock pulse, and with respect to that clock pulse, the two devices are communicating with each other. Now, assume at some point of time, when the communication is happening, this microcontroller 2, who is behaving as a slave right now, gets some very important task. Okay, so very important task. Microcontroller 2, who is behaving as a slave, gets a very important task. It is just behaving as a slave in this communication, but it is a master in fact, and it has got so many other things to be taken care of. So microcontroller 2 is actually behaving as a slave, but as I said, it has got so many other tasks to be performed. So assume when the communication is happening between the two microcontrollers, the one which is acting as a slave is getting a very important task. Assume that very important task is maybe the temperature of the board is very high, that this microcontroller should go and it has to turn on the fan. Okay, that's the very important task. Now, microcontroller 2 has to convey microcontroller 1 that it has got some very important task and it has to go take care of the task, and then it is going to resume back in the communication. Now, what it does is this microcontroller 2 will stretch the clock pulse. Okay, so stretch the clock pulse and keeps it low. Okay, so it is not generating the clock pulse. Whatever clock pulse is already generated, it is going to stretch the clock pulse as stretch the clock pulse, and it is going to keep it low. So it is going to continuously make the clock pulse generate a low signal itself. Now, if it is low, if the clock pulse is low always, Okay. So low signal is always to transmit the data. Okay. Low signal is used always to transmit the data. So when the clock pulse is continuously low, maybe a microcontroller 1 will be able to transmit the data, or whoever is there is able to transmit the data. But do you think the receiver will be able to receive the data, whatever is being transmitted, if the clock pulse is continuously pulled low? No. So for the receiver to receive the data, clock pulse should be at the high level. But if the clock pulse is continuously at the low level, the receiver will not be able to receive the data. So this microcontroller 2 keeps the clock stretched for a certain duration as long as it takes its time to complete the very important task. And once the very important task is completed, so the microcontroller 2 comes back and resumes the clock pulse generation. That is something called as clock stretching. You can see, so clock pulse gets generated, data transmission has happened. So communication is happening. So in the data line, data is transmitted, acknowledgement is being exchanged, everything is happening. Now, after some point of time, microcontroller 2 is getting some very important task, but it is acting as a slave. So what it does is, it is going to pull the line low. It keeps the clock stretched for a certain duration. At that time, microcontroller 2 goes and completes its task, whatever is left pending. So after that, it comes back and it allows the microcontroller 1 to generate the clock pulse normally, and the rest of the communication is going to continue as it is. So that is clock stretching, which happens when when two microcontrollers are communicating with each other. But microcontroller 2 should become master, right, to communicate with other while paused. Yes, so it becomes master. See, a duty of a master comes only when there is a clock pulse required. So it doesn't have to behave as a master, it just has to finish some other task to happen. Or even if it has to turn out to be a master, so master is required when it has to generate a clock pulse. Now, like to turn on the fan, to carry out some simple task, it doesn't have to generate a clock pulse. But even if it generates a clock pulse, it is for some other action. It doesn't affect this communication as such. Okay. Okay. Slave can also transmit its bidirectional data line. Yes, slave can also transmit. Previously, we saw the example itself, right? RTC was transmitting the data in the second register. So slave can also transmit the data. Understood what is clock stretching? Okay. So next one again is something called as clock synchronization. Okay. And I will be able to explain clock synchronization with only the pictorial representation. So let me do this. Okay. Now clock synchronization is another concept which again happens when two masters are communicating at the same time. Is there any timeout for how long master can wait for the slave to resume? So generally, until like the master who is acting as a master is not getting very important task that it has to break the network, so it keeps waiting for the microcontroller 2 to come back. Okay. Now the next one is clock synchronization. Okay. Now what is clock synchronization is? This happens only when two masters start communicating at the same time. two masters start communicating at the same time. Please ignore the mistakes. So I'm going to say that the clock synchronization happens when two masters start communicating at the same time. Okay. Now what happens is, assume not two masters start communicating at the same time. It need not be the two masters start communicating at the same time. It might also be when two masters communicate with each other and both of them want to behave as masters itself. So both of them will end up generating the clock pulse. Now assume I have one master, that is microcontroller 1, okay, generating a clock pulse. I also have microcontroller 2 generating the clock pulse. Now scenario number 1 is, luckily both the microcontrollers started generating the clock pulse at the same time of the same frequency. Okay, it's luck by chance. It is not going to happen every time. So both the microcontrollers started generating the clock pulse at the same time of the same frequency. Okay, so what you end up seeing at the end of the clock pulses, let me complete drawing this. So it's like this: both the microcontrollers started generating the clock pulse at the same time of the same frequency. So I'm going to copy this and paste it like this. Okay, so both of them started generating the clock pulse at the same time of the same frequency. So what you see as the resultant is this. So what you see at the clock pulse as the resultant on the SCL line is this. So what happens? 0 and with 0 is a 0, 1 and with 1 is a 1, 0 and with 0 is a 0, 1 and with 1 is a 1. Now what happens is, when the two microcontrollers, this is in fact microcontroller 2, not microcontroller 1. So both the microcontrollers started generating the clock pulse of the same frequency at the same time. So luck by chance, they both synced with each other. Now when the microcontrollers look at the clock pulse in the actual clock line, okay, when they look at the clock pulse in the actual clock line, they feel as if it is their own clock pulse being transmitted in the clock line. So microcontroller 1, when it sees the clock pulse in the clock line, it assumes as if it is its own data being transmitted. Again, if microcontroller 2 sees the sees the clock pulse in the clock line, it feels as if it is its own clock pulse being transmitted. Now at this point of time, both of them will feel as if it's their own clock pulse being transmitted in the clock line, and they both continue to generate the clock pulse as long as they are using the data line. So this is a form of cheating in fact. So both of them are not coming out of the communication protocol, and both of them are trying to generate their own clock pulse and trying to send it on the clock line. So this is in fact considered as cheating. But this is a very rare scenario. Now assume I have one more scenario where microcontroller 1 is comparatively faster. So it is going to generate the clock pulse for every uh, 0.5 milliseconds. Let me copy the same. So this is the clock pulse of the first microcontroller. Okay, so I'm taking few more clock pulses. This is the clock pulse of the first microcontroller. Okay. So this is the clock pulse of the first microcontroller. Assume the first microcontroller is working with a larger frequency, I mean the higher frequency. So it is taking approximately 5 milliseconds for every pulse. In fact, 10 milliseconds overall. So 5 milliseconds of on period and 5 milliseconds of off period. So assume that is the clock pulse being generated by the first microcontroller. Now the second microcontroller is also generating a clock pulse, but comparatively of a lower frequency, because assume that second microcontroller is slower. Okay, so it is going to generate the clock pulse with an on period of 10 milliseconds, off period of let's say another 10 milliseconds. So this is the clock pulse being generated by the second microcontroller. So what do you get to see at the final clock pulse is the question, because there is only one clock line and there can only one signal being transmitted in that particular clock line. Okay, so now what happens is the second microcontroller is approximately taking 10 milliseconds for the on period and 10 milliseconds for the off period. Now we have to understand what exactly gets transmitted in. One bit of microcontroller 2 is transmitting more than microcontroller 1. Okay. So first what happens is microcontroller 1 generates a low signal. Okay, a low signal for the first 5 milliseconds. Now microcontroller 2 generates the clock pulse for the first 5 milliseconds, but it has to generate the clock pulse for 10 milliseconds. So it continues to generate the clock pulse for another 5 milliseconds at the low level itself. Always remember, low level plays highest priority, highest prominence when compared to that of a high level. So forcefully, microcontroller 1 will also continue to keep the line low itself. So what you get to see in the first 10 milliseconds is a low signal. So first microcontroller 1 transmitted 5 milliseconds of low period. Microcontroller 2 generated 5 milliseconds of low period. But according to the rule, it has to generate the low signal for 10 milliseconds. So it continues to pull the line low for another 5 milliseconds. Okay, and you are going to see a low itself. Now after 10 milliseconds, microcontroller 1 pulls the line up. Sorry, microcontroller 2 pulls the line up. Now microcontroller 2 should transmit a 1. It has to generate a 1. So microcontroller 1 is already hungry. Microcontroller 1 is going to generate a high signal. Okay, microcontroller 1 generates a high signal for 5 milliseconds. Now, the microcontroller 1 always generates the signal for 5 milliseconds only. After 5 milliseconds, it pulls the line low. Okay, after 5 milliseconds, it pulls the line low. So, what you see at the clock pulse is a low signal. Okay, a low signal. So microcontroller 2 also pulls the line low because of microcontroller 1. Now microcontroller 1 generates a clock pulse of 5 milliseconds. So microcontroller 2 also continues to generate the clock pulse of 5 milliseconds. So clock pulse of 5 milliseconds will be generated. But according to microcontroller 2, it should always generate the clock pulse for 10 milliseconds. So it is going to keep the line low itself. So this is what you see because of the microcontroller 2. Then microcontroller 2 pulls the line up after 10 milliseconds. Then microcontroller 1 is eager to generate a high level. So high level gets generated by microcontroller 1. Okay, so something like this, microcontroller 1. And this is what you end up seeing at the clock line of the communication when two masters start to generate the clock pulse of their own. And if you observe here in this representation, the high signal is always taken from the first microcontroller's generation, and low signal is always taken from the second microcontroller's generation. So it's a combination of both the microcontrollers what you get to see in the clock line. Understood this? Ma'am, resulting high speed should shift to right by 5 milliseconds. Uh, See, what happens is, in case of I2C communication protocol, 0 is called as the dominating bit. So whenever there is a chance for a 0 to get generated, the priority is always given to 0. So if any of a pulse, any of a clock is generating 0, when it has to continue to generate a 0, so it is always given a highest priority. Okay. And this is what you get to see at the clock pulse. You can observe here the same is represented in the slide as well. Understood what is clock synchronization? Okay. The next thing we have is data arbitration, as in when two microcontrollers start to communicate at the same time, there is only one data line. So assume two microcontrollers start communication at the same time. Start communication at same time. No, ma'am, in Paint, I think it should shift to right by 5 milliseconds. Sorry, 1 second. I didn't get your doubt. Chaitanya? Where should it shift? See, what happens is you don't see the AND operation happening here. Resulting high signal should be shifted to right by 5 milliseconds. Why? So I saying it has to be like, do you think from here it has to start the low signal? Is that what you are asking for? Don't consider the logical, don't see it as the AND gate. So this is not, you can expect, it is not because of the AND gate. The synchronization is not the exact AND which is happening. The synchronization happens between the two clock pulses when they are trying to generate, when they are being generated by two different masters. Okay, fine. Now coming to the data arbitration. So two microcontrollers start communicating at the same time, but there is only one data line which can be used. Okay, so there is only one data line which can be used. Two microcontrollers start to communicate at the same time. Now, because there is only one data line, there can only be one master who can continue to transmit the data or continue to communicate. So out of the two microcontrollers, only one master is going to win the bus. Now, who is going to win the bus is a question, and that depends on the data being transmitted. Assume microcontroller 1 has the data like 1111 or 1111 0111. This is what microcontroller 1 transmits. Microcontroller 2 has some other data to be transmitted. So let's say 1101 and 0101. So this is what microcontroller 2 will have the data to be transmitted. Now microcontroller 1 transmits 1, microcontroller 2 also transmits 1. So 1 and with 1 on the SDA line, you get to see 1 being transmitted. Then microcontroller 1 transmits a 1, microcontroller 2 transmits a 1, 1 and with 1 will be a 1. So on the SDA line, what you get to see is a 1. So both the microcontroller assumes as if it is their own data being transmitted. Now microcontroller 1 transmits a 0, microcontroller 1 transmits a 1 and microcontroller 2 transmits a 0. What is 1 and with 0? So it's a 0. Now on the SDA line, both the microcontroller sees a 0. So microcontroller 1 understands it is not its data being transmitted on the data line. So it understands that there is some other microcontroller who is already won the bus for the data transmission. So this microcontroller 1 comes out of the data bus and it stops communication. Microcontroller 2 continues to communicate in that particular bus. So that is data arbitration. So representing which microcontroller is going to win the bus when two microcontrollers start to communicate at the same time. So that is data arbitration. Whichever is having the lower data to be transmitted is going to win the bus. So in our case, between the two microcontroller 2 had the lower data to be transmitted. So microcontroller 2 wins the bus and continues to communicate in that particular network. Okay, so that is data arbitration, which happens when two masters start communicating at the same time. Next one, this is the complete data transfer. So first clock pulse gets generated, then data line will be seen. So at the first clock pulse, okay, at the high signal, but due to this case, data may change sometime, right? No, data will not change. So depending on the data is like it is either a 0 or a 1. Okay, whichever has a 0 to get transmitted earlier will win the bus. So that microcontroller will continue to communicate in that network. Okay. All right. So proceeding ahead. So next one we have is the complete data transfer. At the first high signal of the clock pulse, so there will be a start bit transmitted. Then in the first 8 clock pulse, 7 bits of address and 1 bit of read or write intention will be transmitted. In the 9th bit, acknowledgement will be received by the master. In the next 8 clock pulse, master is going to transmit the second register's address and it is going to receive the acknowledgement. And in the other next 8 clock pulse, the RTC is going to transmit the second register's value and acknowledgement will be received by the master. And at the end, stop bit will be transmitted to represent the stop of communication. Saurabh, you have a doubt? Please ask. Okay. So that is the complete data transfer which happens in this communication. That is especially when microcontroller has to communicate with the RTC. Understood this? Okay. Meanwhile, Saurabh is giving the doubt. So let us also speak about the bus direction. So whatever bus you have taken to achieve half duplexity, it's a bidirectional bus. But there are possibilities that you can configure it as a unidirectional bus also. When there is only one way communication to happen, you can configure it as a unidirectional bus also. Now in the bidirectional mode, you have 4 different speeds to be achieved. The standard mode helps you transmit the data for 100 kilobits per second. Fast mode can transmit 400 kilobits per second. Fast mode plus can transmit 1 megabits per second. And high speed mode can transmit 3.4 megabits per second. And in the unidirectional bus mode, you have ultra fast mode where you can transmit 5 megabits of data per second. Now, different microcontrollers support different modes. So, depending on the available mode, the configuration has to be made. And all of this are going to make use of push-pull drivers, so no pull-ups required. So, this is this bus speed and different modes in which the bus is going to work. Any doubts? Okay. If acknowledgement is to be transmitted, its write bit so will happen at the low level of the clock. But didn't clear will master and slave give acknowledgement by pulling the data line differently? If yes, how? So yes, actually acknowledgement is something which is given at the low. See, it is right obviously, but it is a special condition. Acknowledgement you don't consider it as a right itself most of the time. So it's considered to be a special condition, and all the special conditions are done at the high level of the clock pulse itself. So at the high level of the clock pulse, when a device has to give an acknowledgement, transmitter transmits a 1 and receiver transmits a 0. That is what pulling the line up or pulling the line low represents. Transmitter transmits a 1 and receiver transmits a 0 at the high level of the clock pulse. So that is acknowledgement. Okay. So this completes the theoretical part of the I2C communication protocol. The next we have got to implement is the example what we took. So we have to read the number of seconds from the RTC and display it on the CLCD. And it is not just RTC, it is not just number of seconds. You in fact have to read number of minutes, number of hours also from the RTC and display the complete time on the CLCD. So that is the project we have to do, and that I'm going to start it from tomorrow's class. So it will take 2 days to do the complete coding. So tomorrow I may be able to finish half of coding, and on Friday I will be able to complete the coding part. If possible, I try finishing it tomorrow itself. Let us see if it is possible, so that I can finish CAN protocol on Friday's class. That is what the plan is. So if possible, I'll complete the coding part in tomorrow's class. It completely depends on how well you are taking the input what I'm providing. Is this project related to the project of car black box? Yes, it is. It is related. So you need the knowledge of I2C protocol. So we will use I2C. We will use UART also in the car black box project. So you need the knowledge of both the communication protocols. Okay, fine. So this completes the theoretical part of I2C, and programming will do it in tomorrow's class. Hope the class has all been clear. Please have your attendance mark before quitting. We continue tomorrow with the programming part. Okay. So here is your QR. Please have your attendance mark. Thank you all. We'll continue tomorrow.